Well, today we're going to be covering the topic of rocketry. And I can tell you, I guarantee, this is one of the most exciting topics that you can bring to your kids. And if you don't believe me, just go into your classroom sometime this fall and say, today we're going to launch rockets, and watch the reaction. The kids are going to be terribly excited about it. It's not just a thing because it's exciting and rockets shoot off, and if you use the commercial ones with the gunpowder engines and so on, you get smoke trails. It's not so much that. It's the fact that they work, they're easy to make, they demonstrate good science, good math, good technology, good engineering. They're all together. It's a very good standards-based activity for your classrooms. And when you may not see it talked about in the standards book about rockets as such, but if you talk about force and motion, there you are. And measurement and so forth, it's all there. It's a wonderful, wonderful topic. So kids get really excited about it. And let's face it, rockets are the only way we have of going to outer space. And kids love space. So, it all comes together. All right. I'm going to start off with a presentation on the science of rocketry to kind of make sure that we all understand about force and motion. Then we're going to do some demonstrations on here. And finally, we'll end up with building the launcher and building the rocket that will go on the launcher. Okay? Well set? All right, good. Well, let's get started right here. And we're going to be talking a little bit about the science, engineering, technology, mathematics of rocketry. Thank you. In spite of the complexity of a space shuttle. I mean, we live here in Houston. We know that space shuttles are a really big deal type rocket. It's very, very complex. But the principle governing this rocket here and all other rockets capable of going to space, it's very, very simple. There are several principles, but they're very simple to understand. And it doesn't matter if you're flying a big rocket or you're flying a small rocket. If you understand those principles, you have mission success. That's the basic message right here. Well, let's take a look at the beginnings. Now, I'm sure you'll recognize some of these pictures from years ago, if nothing else. These are two of some of the most famous scientists that have ever been out there, scientists of the past, Galileo and Isaac Newton. And it turns out that Newton was born on the same year that Galileo passed away. These two men have helped to lay the foundations for rocketry. Now, Galileo is actually a mathematician. He was the one that developed the astronomical telescope, although he didn't invent the telescope itself. He just was the one that first used the telescope to look up at the stars and things. Newton is the person that's famous for force and motion, calculus, all kinds of different things. The visible spectrum, he was able to break up light and so on and so forth. I mean, these two guys have done a lot. Well, first off, Galileo, he talked about motion a lot. He spent a lot of time studying motion. And you may remember the Leaning Tower of Pisa. Supposedly he dropped a big object and a small one. They both fell at the same rate, all kinds of things. His main idea was that in order to do science, you didn't think it through. What you did was you tested it. Because prior to him, a long time ago, the Greek Aristotle would figure things out in his head, write them down, everybody would believe they'd be true. Like, for example, if you had two objects, one weighed 10 times the amount of the other object, the one that weighed 10 times as much would fall 10 times faster. And boy, that made a lot of sense. Until Galileo tried it, didn't work that way. They both fell at the same rate. So, I mean, you have to test. Well, that's what Galileo did. But here, he did come up with the idea of inertia, which is the property that all objects have. You have a force built in. You might call it like a force, but it's a resistance to changes in motion. This lady sitting right here is going to sit there unless she either exerts a force herself or I come along and push her. But if I push on her, she's going to resist. Without even trying, her body will resist my push. That's called inertia. Once she gets going, then her body wants to keep going. That's inertia again until some force stops it. And that's the reason why if you're running down the hall and you're kind of late for class and you walk into a wall, it hurts. Your body inertia is what causes you to mash into the wall. You still want the... If you have a chance, yeah, sure. Thank you. Okay. All right. Isaac Newton, he followed along. He came up with what people really call the greatest science book ever. And don't bother trying to read unless you can find a translation. It's all in Italian, or it's all in Latin, rather. But his book came up with the three fundamental laws of rocket motion. So we're going to see about those three laws. Get ready for launch. Here we go. That's his book. They call it Principia. And the first law of motion is somewhat of a lengthy kind of a law, but it's very simple, really. Once objects that are in motion will stay in motion, or objects at rest will stay at rest unless acted upon by an unbalanced force. It's also known as the law of inertia. It's Galileo's law, or the idea Galileo had. Now, what does that mean? Well, first off, we better understand what's an unbalanced force. You got these two, I guess, rugby players pushing on each other. Each player has an equal mass, so they're pushing. And they don't go anywhere. Equal mass, equal force, you know. Okay, but what if we unbalance the force? That's what is meant by it, unbalancing the force. That's all we're talking about. Very simple idea here. Okay, now I'm going to go over here because I think my microphone may pick up the sound. These little speakers are kind of weak. So let's take a look here. Now we got something different here. You probably heard that, okay? So, same force, though, different result. Why was there a different result? The elephant, which one had more mass? Okay, the elephant has more mass. Which one then would you think would have more inertia? Yeah. Inertia is really kind of based on the idea of mass. If you got a lot of mass, it takes more to get you going than if you have less mass. Try to push a Volkswagen Beetle versus a semi-truck that's installed, you know. The one with the more mass is harder to push, more inertia. And the same thing here. So this is part of this whole idea of inertia. The more mass you have, the more inertia you got. Either resisting motion or once you're moving, it's harder it is to stop you. So the elephant has a greater mass than the mouse. Now, why are we using mass instead of weight? Well, this is just a scientific thing, really. Here's an example. Weight changes depending upon your environment. We got an astronaut standing on the moon, on the Earth rather. And the astronaut weighs 360 pounds. That includes the spacesuit. And spacesuits are very heavy. They weigh close to 200 pounds. So it's a pretty heavy garment to wear on Earth. Okay, on the moon, or actually in orbit, that spacesuit weighs 0. And the astronaut doesn't weigh anything either. So you can say they're weightless. And on the moon, because gravity is a good deal less on an Earth, look at now. The suit weighs only about 60 pounds. When you see the video of Armstrong and Aldrin on the moon, bouncing around and so forth, having a great time, they're not falling back to the ground as fast as they would if they were doing that same thing on the Earth. You know, the gravity is less there. Okay, so weight changes. But if you talk about mass, on Earth, the mass is 164 kilograms. In free fall, it's 164, and on the moon, it's 164. So it doesn't matter. Mass is just the amount of matter a body contains. That's all it is, and it doesn't change, but your way of measuring it may change, depending upon the gravitational environment you're in. So if you went to the sun, you'd weigh several times more. If you could stand on the sun, you would weigh several times more than you would on Earth. I mean, it just depends upon the body. Okay, so it takes the same amount of unbalanced force to change your state of rest or motion, whether you're on Earth or in free fall or on the moon. It still takes the same amount of force. Now, here's the implication of this first law. It's a very powerful implication. We're talking a lot about, you know, cost of gasoline and travel and, you know, saving energy and so forth. That rocket there uses one heck of a lot of fuel to lift off. And you might say, that's terrible. I don't even know how much it is, but, you know, it filled this room up with fuel easily. Okay, Voyager 1 launched 1977. The spacecraft is still traveling today. It's more than 15 billion kilometers from the Earth. It's going 17 kilometers a second. And all of the propulsion, all the power used to move this rocket was expended on the first day of launch. After that, in space, because of its inertia, it's been coasting ever since. I don't know exactly what the miles per gallon is, but it's probably in the 100,000 miles per gallon right now. And the longer it stays out, the longer it travels, the mileage gets better and better and better. Because all you need to do is get it going, and then it keeps going. First law of motion. Objects in motion will stay in motion unless acted upon by an unbalanced force. Now, the path of the Voyager will bend depending upon if it comes near anything. The gravity will bend its path, but it'll just keep going and going. We expect this thing to be out there for 40, 50,000 years maybe. Eventually, interstellar dust may wear it away. Who knows? We're so confident that it's going to travel way out there. We've actually put on board a, well, it seemed like great technology at the time. It was a big video disc, and it had pictures of people and stuff on this thing to tell what Earth is like and sounds and everything else. You're assuming, of course, that somebody has a video disc player out there if they ever find this thing. But that was kind of a cool thing to do. So this is the implication of that first law. Very powerful implication. Newton's third law is the one that people generally know. They may not be able to say it, but basically it's action-reaction law. For every action there is an equal but opposite reaction, meaning that the action's one way, the reaction's the other way. Simple concept. Okay, let's take a cannon, which is actually one of the best ways to show this. So you get this heavy cannon, old Civil War side or style, or maybe Spanish Armada kind of cannon. I don't know which one it is. But it's loaded with black powder. It's got a cannonball in there. The fuse has been lit, and I hope the sound will work. Well, I'll go boom. The cannon fires. Now let's make sure we got that right, so we'll have an instant replay. Just barely hear it there, but it did fire. Those speakers must be running out of battery power. Here's what's happening. The cannon starts right there, and it rolls backward that way. The cannonball starts right there. It flies out this way. So we have opposite directions. The action is the cannon going this way. The reaction is the cannonball going that way. But look at the difference here. Now let's go back a little bit. First law of motion, inertia. Which of these two have the greater mass, that one or that? Okay, the cannon. So it has more inertia, and as a result, when you have this explosive force, the black powder blowing up there, it's going to move the cannon a bit, but the cannon is resisting more than the cannonball. So it rolls back a short distance. But the whoops, I hit the wrong button. But anyways, the cannonball itself has less mass, and it has the same force. The force was the same for here, for the cannon and the cannonball. It has less mass, so it travels farther because its inertia is less. So it flies away. And when you watch all those movies, like the Civil War movies and so forth, or watching the pirates do this stuff, the cannons, they fire them, they all roll backward, and the cannonball takes off and hits the other ship, That's what's going on here. And that's basically the principle of a rocket. And we just saw a rocket go by there, but in our rocket, you have had, I'm going to back this up here. Maybe I can get the rocket to come back. Okay, try it again. Boom. There we go. There's our rocket. In this case right here, the rocket is the heavy part. The exhaust, the fire coming out the back, smoke, gases, and everything else coming out the back, that's like the cannonball. And you might say, well, wait a minute, the rocket really travels. Well, I'll tell you, yeah, it does. Only because of one big difference. The rocket doesn't stop firing when you go boom. It's not over. It keeps going and keeps firing and building up its speed. If you watch a space shuttle on the launch pad take off, you're standing watching the movies or whatever, this thing kind of creeps up off the launch pad, and it's going faster and faster and faster, and away it goes. It takes a while to get it there. But the funny thing about it, you can't tell this from the movies or watching it on television, but by the time the space shuttle goes from the platform it's on till it clears that metal structure, it is already traveling 100 miles per hour. And the thing is, you can't tell it because of the size and the distance. You can't see it, but it actually is going that fast. Within like 2 or 3 seconds, it's already going that fast. And the astronauts are in their seat are being pushed back. They feel 3 times heavier than they would feel normally because of their inertia pushing them back into the seat. Okay, second law of motion. I'm skipping here. I went from 1 to 3. Now I'm going to go back because this is the one that kind of describes it. I would have preferred this be number 3, just to be nice and order. And this one sounds kind of complex. The acceleration of an object is directly proportional to the net force acting upon it and inversely proportional to the mass of the object. Well, you can play with mathematics, when you get inverse things and so forth, flip them around a bit, and you end up with this equation down at the bottom. It says F equals ma. The force is equal to the mass times acceleration. Now, what does that mean? All right. Back to our cannon. Remember, the cannon had a really big mass. The cannonball had a very small mass. When the cannon fired, the acceleration of the cannon rolled back a bit, and the cannonball took off. So here's how it goes. Force is the explosion equals mass times acceleration. Big mass means a small acceleration. Small mass means a big acceleration. It's a very simple equation, really, think about it. So here we go again. We'll take another look at this. Oh, I hit the button I shouldn't. There we go. Here we are. We got our big mass. The acceleration is small. And we got a small mass coming out the back end, but shooting out like crazy. Big acceleration. If you keep it going, keep shooting more and more and more, keeping it going for minutes, this rocket begins to pick up speed and go faster and faster and faster. And that's really how it works. Even though it's a light amount of mass coming out the back, it goes out fast, and you give it plenty of time, and it builds up its speed. And it's the same thing with your cars. You're sitting at the intersection. You put your foot down on the gas pedal. You don't shoot away at 30 miles an hour or whatever speed you like to go at. You shoot out. You pick up speed, gradually accelerating. It takes a little time for your car, but you keep the foot on the gas pedal, and you build up your speed. Same thing with the rocket. Okay, we're going to do a little rocket scientist tricks here, because there's a lot of cleverness involved in building a rocket that can actually go to space. I mean, anybody can build a rocket, but to get up there takes a huge amount of energy and a whole lot of smarts. And it used to be they'd say, when they compliment somebody for being very smart, they refer to you as a rocket scientist. I mean, that was an old line there, and people took that very seriously. Then, of course, if a rocket blows up, they look at the rocket scientist and kind of roll their eyeballs. Rockets are tough. They're hard to make work. They're very, very complex when you really get down to it, but the ideas are simple. Okay, here's one of the ideas. We call this staging. Now, staging basically is, instead, if you want to go to space, why carry a big empty rocket shell to space? When the big bottom part of the rocket is empty, why not just let it go and then let the rest of it keep going on to space? So this is the idea of a staging. Each stage here is actually a rocket by itself. That's the first stage right there. And then you got a second stage, which is a rocket. And then the third stage, which has up on the top a little payload, might be a satellite or an astronaut or something. Okay, let's have our launch right here. So we fire that rocket. It's climbing and climbing. The first stage gets empty. Drop it off. Second stage fires. It's empty. Third stage fires. That's the idea behind this. So therefore, you can get your payload up there because the rocket becomes more efficient each time you drop the heavy pieces off that are empty and no longer doing anything. That's one of your tricks. And take a look at this Delta rocket right here. We'll mark off all the parts. You got your first stage, that's the core right there, and you got two strap-on boosters right there. You got your second stage, you got your third stage, and then the payload. And some of these boosters here, actually, they'll have as many as 9 on the outside down there. And first thing that happens, they take off, and those boosters start to fall off after you get going. Then the first stage falls off, and so forth. Okay. Here's another trick, and I mentioned it before. You got this hollow section inside the rocket, and all you do is you burn the entire surface of that, and it burns not just from the bottom up, it burns from the inside out. And that increases the surface area that burns, so you get more burning and more gases coming out the back, so they go out faster as a result, and you get better thrust. But you can even get more clever than that. You can do this. You can make a hollow core that looks like a star shape. And all those little edges have more surface area, and they really burn like crazy. In the solid rocket booster for the shuttle, they use that idea there to help increase their thrust. You can try different kinds of rocket fuels. That's another trick. And liquid fuels are really nice because once you start a solid fuel up and you say, whoops, we didn't mean to launch just then, it's too late. You're going. The rocket fuel burns. But with the liquid one, you can just turn off the valves. And it shuts down, and the thing sits there. There have been cases where the engine just started to fire and they had to shut it down within a half second of liftoff because they detected a fault. That's one good thing. You can start them and stop them up in space, too. Very nice. Liquid hydrogen, liquid oxygen, one of the many combinations they use. Well, here are some different kinds of rockets. You got your solid propellant. You got your liquid propellant. Then this one has never been built, but it's called a nuclear thermal. And what it has is a big tank of liquid hydrogen gas, and then it has a nuclear reactor for a rocket engine. And the reactor simply gets really, really hot. The hydrogen gas passes by it and gets very hot. The heat transfers over to it, and it shoots out the back. Basically what it is a nuclear-powered balloon. All it does is blow the gas out the back, and away it goes. It's a great idea on paper. Hasn't happened yet, but we're looking at it. Then there's one that has been worked on, ion propulsion, which is, they call it electric rocket. You'll notice it has solar panels on the side, and it has a small propellant tank. And what they do is they ionize an atom like mercury or cesium. So different elements can be used. And they turn them into ions, which are electrically charged atoms. You strip off electrons, in other words. And then they're magnetic when you strip off those electrons. So you have a magnetic field. They're shot out the back with magnetism, and it propels the rocket. Now, these have been used, but they're used mainly for little thrusters to help kind of aim the rocket in the right direction in space. But they're not very, very powerful. You couldn't use them to lift off of Earth. They're only working right now as well enough to do flight once you're in space. But there is a former astronaut, Franklin Chang Diaz, who has had, I don't know if he still has his laboratory here in Texas, but over by the Johnson Space Center. He's been working on a rocket that could propel people to the moon, to Mars. And he believes that if his engine can ever get to its maximum theoretical potential, using an electric rocket now, he figures that instead of a 7-month trip to Mars, it would take only about 39 days. So that's pretty exciting. If that ever happens, we're going to have short trips to Mars. And that really is important because that's a long way out there, 7 months in space in a radiation environment. The shorter the better. All right, so what else we got here? Another thing here. you know, thrust will increase as outside atmospheric pressure decreases. That's something that's kind of neat, too, about rocketry. Here's what we mean. On the ground, you got atmospheric pressure pushing up inside the rocket. Same time, the rocket firing is pushing out, and they fight each other. And if it turns out the inside pressure is the same as the outside pressure, you don't get any thrust. You have to have greater thrust to get that. And it pushes out kind of slowly. But as the rocket lifts off, the air gets thinner, so its pressure gets less, too. When you get up in space, out it comes. So rockets actually work better in space than they do on the ground. Here's another thing. Change the shape of the rocket engine nozzle. Good old garden hose here. Water pours out. F equals ma. But if we could make the water go faster by making a nozzle, we get a greater force. Here's the variation with a shuttle engine. Take a look at this. You've got, that's the engine right up there, but this narrow part right here forces the gases to come shooting out at a high speed. That increases the thrust. Well, we're going to have our rocket scientist review, and then we're going to start doing stuff here. And a couple of quick questions here. Well, not questions, but statements. This has to do with the first law of motion. Unbalanced force is needed to start the rocket moving. So you got this rocket in the pad, needs an unbalanced force to get going. Once moving, it keeps moving, okay? Second law, the amount of force is determined by this equation, F equals ma. And I'll just leave that, I'll pass over that fast here. And then the third law is the action-reaction. The gases go down, the rocket goes up. That's all the laws that we're really talking about. Now, you can get very mathematical if you want to, but that's really the basis of rocket motion. Okay, and we are now ready for liftoff.